Artificial turf can become the stage for a historic golden goal, but it can also be the cause of a career-ending slip. That life or death difference is decided inside the factory, where a closed production line turns rough plastic pellets into a soft green carpet. From melting and drawing high-strength fibers to tufting and protective coating, every link must be absolutely precise, because just one small mistake can instantly turn the field into a dangerous injury trap. Join Factron Process as we step inside a modern industrial production line to uncover the secret behind FIFA-quality artificial turf. Artificial turf was developed to solve the shortage of green space at inner-city schools, but the invention only truly entered the world stage in 1966, when natural grass inside the domed Houston Astrodome kept dying due to lack of sunlight. The entire field was replaced with a new material. The name AstroTurf was born, and from an emergency solution, artificial turf quickly spread across stadiums in the following decades. Today, the artificial turf manufacturing industry is worth about $7.3 billion in 2025, while the sports turf market alone generates more than $2.26 billion. This material now covers not only football fields, but also schools, playgrounds, gardens, hotels, and many urban projects. A FIFA quality field is even designed for a typical usage frequency of around 40 to 60 hours per week. The process begins with small polymer pellets, mainly polyethylene and polypropylene. These synthetic materials are flexible, elastic, and resistant to outdoor conditions, which makes them commonly used to create artificial grass fibers. The pellets must be stored in a dry and clean area. Even a small amount of moisture can turn into steam when the material enters the extruder. But clear plastic pellets alone are not enough to create an outdoor grass blade. The factory must add green color master batch, heat stabilizers, processing aids, and additives that resist ultraviolet radiation. Materials are weighed according to the formula and fed into a mixing unit. Once the mixture is uniform, it is transferred to the most important step in forming the grass blade, fiber extrusion. The plastic pellet mixture is fed into the extruder, where a screw continuously compresses, mixes, and heats the material. Across different heating zones, the pellets melt into a uniform polymer stream, then pass through a filter to remove impurities before being forced through a shaping die. Depending on the design, the die can create separate monofilament fibers or a thin film split into many narrow strips. The fibers leaving the die are still hot and soft, so they are immediately guided through a cooling water bath to stabilize their shape. The fibers then pass through roller groups, rotating at different speeds. The rear rollers run faster, stretching the fibers and helping the polymer chains align more orderly, making the fibers stronger. Finally, the fibers are evenly wound onto cores with stable tension before being moved to the combining and twisting area. The finished yarn rolls are placed on support frames, then the fibers pass through tension control units to be combined or twisted according to preset parameters. The goal is not to twist them as tightly as a rope, but only enough to keep the fibers from separating, tangling, or catching during high-speed feeding. Depending on the carpet design, some monofilament fibers can be fed directly, while others are combined into bundles so they spread more evenly on the surface after tufting. Once stable, the yarn rolls are placed on a large metal frame called a creel. From each roll, the yarn end passes through tubes, ceramic eyelets, and tension controllers before reaching the tufting machine. This system can feed hundreds of yarn bundles at the same time, matching hundreds of needles on the machine. The primary backing is laid flat and fed continuously into the tufting machine, a device that works like a giant industrial sewing machine. When the machine runs, hundreds of needles push the yarn bundles through the backing at the same time, while hooks underneath hold the yarn to form even loops. Depending on the design, these loops can be left intact or cut open by knives to create separate, upright grass blades. After each cycle, the backing moves forward, allowing each row of yarn to form one after another into a continuous carpet. The row spacing, fiber height, number of fibers in each bundle, and backing feed speed determine the thickness, density, and stability of the turf surface. Just one block needle, broken yarn, or change in tension can create a missing line running across the entire carpet. The turf is guided through a coating system, so latex or polyurethane can spread evenly over the back and surround the fiber roots. A doctor blade and rollers control the coating thickness, because a layer that is too thin will not hold the fibers well, while one that is too thick makes the carpet heavy, stiff, and less able to drain water. Some products are also laminated with a secondary backing to limit stretching, wrinkling, or deformation. The carpet then passes through an oven or curing chamber, where heat forms a strong bonding layer. Temperature and time must be controlled to prevent uncured adhesive or backing shrinkage and warping. After this step, the fiber roots are locked in place, but the back is more sealed, so the carpet needs perforations to let rainwater drain down into the base. The turf is guided into a punching machine, where needles, pins, or punching mechanisms pierce through the backing and the cured coating layer. The holes are arranged at repeated intervals across the entire roll. The goal is to allow water to pass through the surface and flow down into the base system underneath, instead of forming puddles. This is a technical balance. Too few holes slow down drainage, but too many holes, or holes that are too large, can weaken the backing and reduce the carpet's stability. Each hole needs a clean edge without tearing the surrounding material. A small tear can expand under pulling force, thermal expansion and contraction, or long-term loading. Not every artificial turf system uses the same drainage design. Some products are perforated across the entire surface, while others use a naturally permeable backing or coating zones arranged to leave water channels. Actual drainage performance also depends on the field base. A carpet with many holes can still flood if the stone layer underneath is compacted incorrectly, lacks slope, or has blocked drainage lines. Once the whole system is complete, the carpet enters the final inspection stage. The excess backing on both sides of the carpet is trimmed with rotary knives or guided blades to create straight edges and consistent width, making installation and field seams easier. Workers then inspect the color, straightness of the yarn rows, missing fiber areas, flattened fibers, and backing condition. Representative samples are also tested for tough bind, recovery, abrasion resistance, color stability, and water permeability. For football fields, FIFA divides certification into FIFA Quality for community fields and FIFA Quality Pro for professional football. However, final certification is assessed on the fully installed field, including ball rebound and roll, force reduction, rotational traction of the shoe, and surface uniformity. Rolls that fail are repaired or rejected, while approved products move to the finished rolling stage. Before rolling, the surface may pass through rollers or brushes to lift fibers that were pressed down during processing. The carpet is then wound onto a paper, plastic, or other rigid core. The system must keep tension even so the roll does not wrinkle, shift at the edges, or slip between layers. Once it reaches the preset length, the machine cuts the carpet crosswise. The finished roll is secured and wrapped in polyethylene or polypropylene film to protect it from dust, water, and friction during transport. The product label records the batch code, size, color, fiber type, and order information. Batch traceability is especially important when a project needs multiple rolls with consistent color. The rolls are transported in a way that limits core bending or fiber crushing. A deep crease in the backing can become a raised point on the field if it is not handled properly before installation. From here, the product leaves the factory, but to become a complete artificial turf field, it still has to go through an installation process that requires no less precision than manufacturing. First, the installation team surveys the area's dimensions, elevation, and drainage capacity. Weak soil or uneven surfaces must be treated first. The base layer is usually made from crushed stone, leveled and compacted according to the designed slope. The rolls are laid in the same direction so the color and fiber lean remain consistent. Adjacent edges are cut straight, placed tightly together, and bonded with seam tape and specialized adhesive. The seam must be strong but cannot overlap. Just one strip laid in the wrong direction can reflect light differently from the surrounding area, making it look like a different shade of green, even when it comes from the same batch. For 3G sports fields, silica sand and elastic infill are spread in layers and brushed down to the fiber roots. Sand adds weight and stabilizes the carpet, while the elastic infill supports playing characteristics and helps keep the grass blades upright. This is also the part of the industry that is changing quickly. Some rubber and plastic granules can migrate out of the field as microplastics, so manufacturers and investors are paying more attention to organic infill, edge containment systems, or designs that do not require polymer infill. After the infill is fully spread, brushing machines pass over the surface several times to distribute the material evenly and lift the fibers. The surface is checked for flatness, seams, infill quantity, and drainage before handover. According to an estimate cited by the Synthetic Turf Council in Henderson, Nevada, replacing natural grass with artificial turf at a school field can save about 2 million gallons of water per year. However, this type of surface is not completely maintenance-free. Operators still have to regularly collect debris, brush the grass fibers upright, top up the infill, clean the field lines, and inspect seams between carpet sections. In other words, it is a lower maintenance surface than living grass, but not a surface that needs no maintenance at all. But from here, a major question appears. If artificial turf is more durable, uses less water, requires no mowing, and can handle around 40 to 60 hours of use per week, why do elite football tournaments like the World Cup still prefer natural grass or hybrid turf? The answer lies in playing feel, surface temperature, shoe grip, ball roll, and the familiarity players develop after thousands of hours training on real grass. In professional football, the surface does not only need to look good, it must respond naturally during every sprint, turn, slide, and landing. That is why, alongside the artificial turf industry, world football still maintains an extremely strict natural grass production process. It begins with selecting grass varieties suited to the climate, usually durable types such as ryegrass, bluegrass, or tall fescue. The grass is then grown on specialized farms for months, continuously watered, mowed, fertilized, and protected from pests before it becomes thick enough to harvest. Once it reaches the required quality, the grass is cut into large rolls with a thin layer of soil underneath to keep the root system stable. For the 2026 World Cup, each field may need around 84,000 to 87,000 square feet of specialized grass, equivalent to more than 7,800 to 8,000 square meters, and must be transported by 27 to 30 refrigerated trucks to keep it fresh before installation. After being laid on the field, the grass usually needs about 1 month for the roots to reattach to the base before match day. Every base layer, drainage system, slope, artificial lighting setup, and maintenance schedule is continuously controlled. If artificial turf is the product of polymers, extruders, and tufting lines, natural grass is the result of high-tech agriculture, pitch engineering, and daily care. It is a completely different journey, where the playing surface is not made on an industrial line, but grown, maintained, and kept alive until match day. That brings our journey through the complete artificial turf manufacturing process to an end. From small polymer pellets, the factory has turned them into durable grass fibers, stretched them for greater stability, combined them into bundles, inserted them into the backing, locked them in place with a protective coating, punched drainage holes, inspected the quality, and rolled the finished turf for delivery to the installation site. Behind the seemingly simple green fibers is an entire system of materials, machines, and precise technical controls. An artificial field does not only need to look green like real grass, It also has to withstand friction, pulling force, sunlight, heavy rain, and thousands of repeated steps every day. That is why every detail has its own role. The grass fibers determine durability and surface feel, the backing keeps the structure stable, the coating locks the fiber roots in place, and the drainage holes help prevent water from collecting on the field after rain. But a good playing surface does not come from the factory alone. After leaving the production line, the turf roll still needs a properly prepared base, a suitable slope, a stable drainage system, and accurately installed seams. For sports fields, the infill material also plays an important role in keeping the fibers upright, creating cushioning and supporting player movement. Only when all of these factors are properly controlled can an artificial turf carpet become a stable, safe, and durable surface for thousands of hours of activity. From school fields and community sports areas to professional football pitches, artificial turf has become an important part of modern sports infrastructure. It does not completely replace natural grass, but it has created a durable, flexible, water-saving solution that can handle a much higher usage frequency than living grass. And for that reason, artificial turf continues to evolve, from fiber materials and backing systems to coatings and more environmentally friendly infill solutions. If you found this process interesting, don't forget to like, share, and subscribe to Factron Process to keep exploring more impressive production lines.